We're going to do an introduction to exponential functions today. Okay, so an exponential function, well, let's just start with an example of an exponential function, the toolkit function, y equals f of x equals 2 raised to the x power. We can start with a table. I prefer to start with a constructed grid within a rectangular window, but it's going to come down to the same thing. Okay, so we have x and we have y equals 2 raised to the x. Now, I'm going to do this for more values of x than you probably really need to put on a graph in order to get a good representation of an exponential function. So I'm going to start with x equals 4 and go down. You see my reason for this in a minute. When x equals 4, y equals 2 to the x. Well, complete this table, okay? And don't plug things into your calculator. Do the calculations and give me fractions when you need fractions. Don't give me decimal equivalents, okay? If you can't do the arithmetic, then, and it's not uncommon that people have trouble with the arithmetic at this point in their studies, then we'll clarify that, but do the arithmetic, okay? And if you're doing this on video, watch. Do this, pause the video, and then come back. Okay? If you do it wrong, we'll correct it. Okay, well, hopefully you've done this. Let's work out the numbers. Okay, y equals 2 to the x, so if x is 4, we're going to get 2 to the 4th. Now, of course, you can put that into your calculator, but it doesn't give you any understanding just to put it into your calculator and get the result. 2 to the 4th means 2 times 2 times 2 times 2. Well, 2 times 2 is 4. Multiply that by 2, you get 8. Multiply that by 2, you get 16. Okay, if x equals 3, what's 2 to the x? Well, it's 2 to the 3rd, which is 2 times 2 times 2. Well, 2 times 2 is 4. Multiply by 2, you get 8. Bad looking 8, but it's still an 8. Okay, if x equals 2, y equals 2 to the x, which is 2 squared, which is 4. I think people understand what the square is, but it's 2 times 2, that's 4. When x equals 1, 2 to the x is 2 to the 1 equals 2. Now, there's a pattern to these numbers. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. Okay, so here we can say 16 over 2 equals 8. So from 16, we could get the value for x equals 3, just dividing 16 by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. So what would 2 to the 0 be? You might or might not remember the rule for raising things to the 0 power. Most people that come into pre-calculus don't, but since we're a good ways into the course, you might well remember what the rule is, but let's just use this. Okay, we start with 16, we divide by 2, we get 8, we divide by 2, we get 4, we divide by 2, we get 2. Well, if we divide 2 by 2, we should get 1. So we ought to get 1. So if we're going to be consistent, we're going to have to say that 2 to the 0 is 1. Now, any number, including 0, raised to the 0 power is 1. That's a hard and fast rule that should have been drilled into you in high school in your prerequisite courses. But we find that it hasn't been in most cases. Okay, anyhow, we can continue the progression. So 1 divided by 2, of course, is just 1/2. So the number we get here for 2 to the negative 1 should be 1/2. 1/2 divided by 2 equals 1/2 times 1/2, which is 1/4. So 2 to the negative 2 should be 1/4. 1/4 divided by 2 is 1/4 times 1/2, which is 1/8. And if you don't know how to do these divisions and do these fractions, you're not going to understand some things that are important to understand. So make sure you do. Incidentally, I wrote 2 to the negative 1 here accidentally. Okay, it's 2 to the negative 2, that's 1/4. 2 to the negative 3 is 1/8. And 2 to the negative 4 is 1/16. And again, that's because 1/8 divided by 2 equals 1/8 times 1/2, which is 1/16. Well, that's more values than we can really put on a graph. And we'll see why that is. Usually when I graph the exponential function, I just take the numbers from 2, the x values from 2 to negative 2, and I construct my graph based on those numbers. So here's the y-axis. Notice that all our y values are positive, so we don't need much y-axis down below the x-axis. Here's the x-axis. I'm going to draw the line x equals 2, and the line x equals negative 1. Then I'll draw the lines x equals 1, x equals negative 1. Okay, now before I do the rest, let me just comment. Open Math often puts 1/2 in here. Here, between 0 and 1, you got 1/2. Between 0 and negative 1, you got negative 1/2. You can't calculate that. You can calculate all these values. So I think there's no sense at all in including 1/2 and negative 1/2 in a table for the exponential function. As you're going to see, we get a very good definition of a graph just from these values. We don't need the 1/2 and negative 1/2 x values. We don't need those y values to do a perfectly good graph. So here we go. But x is, this should have been x equals negative 2. Okay, our y values go from 1/4 up to 4. Of course, we've already got y equals 0 on the x-axis. So if we go up to x equals 4, or y equals 4, we'll put that line right here. Okay. Now, when x equals 2, y equals 4. So we do the point 2, 4. So there's our point 2, 4. When x equals 1, y equals 2. Now, where is 2? If y equals 4 up here, where is y equals 2? Well, it's halfway between 0 and 4, which will be halfway between the x-axis in the y equals 4 line, which will be about on this line. Here's our y equals 2 line. And this point then is the point 1, 2. Then when x equals 0, y equals 1. Well, where's y equals 0? Well, it's halfway between 0 and 2. Let me just write in. We don't need to write y equals 0 for the x-axis because we know that. But surprisingly, people at this stage are still kind of forgetting that. Okay, so the halfway between y equals 0 and y equals 2 would be about here. So that's for y equals 1. And then the point x equals 0, y equals 1 is here. When x equals -1, y equals 1/2. Well, where's 1/2? It's halfway between 0 and 1, which is going to put it in about here. So when x equals -1, y equals 1. So that gives us the point -1. Y equals 1/2, sorry. -1, 1/2. This point, I didn't label this point, it's 0, 1. And then when y equals -2, when x equals -2, y equals 1/4. Where's 1/4? Halfway between 0 and 1/2. So here's the line where y equals 1/4. And there's a point on our graph. Now, if we wanted to go to -3, we do 2 to the -3rd, which is 1/8. We'd have to draw a line halfway between 0 and 1/4 to see where 1/8 is. Well, it would be down about here. And we could go to x equals -3. And we could say, okay, yeah, there ought to be a point about here. And then we got to go, if we want to go to -4, we got to go twice as close to the x-axis as this. And it's going to get difficult to draw that. Now I've got the y equals 0 label in the way, but you understand that if we go much further to the left, we're not going to be able to squeeze another line in. Okay. Again, our lines for our y values are 4, 2, 1, 1/2, 1/4. So here's y equals 4, here's y equals 2, here's y equals 1, here's y equals 1/2, here's y equals 1/4. We're always going halfway to the x-axis. All right, well, we can draw a line or a graph, a curve, a nice smooth curve through these points. And if we've got a reasonably well-constructed graph, it's very easy to draw a nice smooth curve that represents the exponential function. We understand that as we keep going to the left, every time we move 1 unit to the left, the y value gets half as great. We've established that. And when we're going from x equals 4, 3, 2, 1, 0, all the way down to -4, we're moving to the left along the graph, 1 unit at a time. And the y value is becoming half as great each time we do that. Then, of course, we could look at it from left to right, and we see that the y value is double every time we go over a unit. We go from x equals -2 to x equals -1. Y goes from 1/4 to 1/2, doubling. And from -1 to 0, y goes from 1/2 to 1, another doubling. And then from 1 to 2 doubles, and from 2 to 4, again doubles. Every time we move over 1 unit, the value doubles. Okay, so that's an important characteristic that's related to one of the defining characteristics of exponential functions. So that's one thing I think it's important to carry with you as you work on exponential functions, because the doubling time of an exponential function is a very important characteristic. Um, and when we study transformations of this function, each one is going to have a doubling time. Okay. Uh, for example, the amount of money you have in an account at constant interest. Okay. Um, it grows exponentially. That is, there's a certain time it takes for it to double. If you have money at, say, 4% annual interest, compounding, it's going to double in about 18 years. The value of your account will double. Now that, let's say the dollar amount of your account will double. Whether the value actually doubles depends on whether inflation is beating your interest rate or not. But understanding exponential functions is very important for that. Um, bacteria growth. You leave food out on your counter, the bacteria grows exponentially. Now, depending what food, you better get it in the refrigerator pretty quick. Some foods last longer than others. Some foods have a much quicker doubling time. Okay. If you double 10 times, you start with y equals 1 when x equals 0, and double again, you're up to 4. Well, if you double that, you're up to 8. If you double that, you're up to 16. Okay. So if we extended this graph a little ways to the right, we could have the line, we'd have room on the board for the x equals 3 value, which would be double the y equals 4. So double 4, you go that far, you go that far again. Up here is the y equals 16 line. If we double again, we get 32, the y equals 32 line. Now that's this much higher than this, which puts it up here about as high as I can reach. If you double that again, it's through the ceiling. Double it again, it's through the roof. Okay. And you double it 10 times, you can work that out. If you double 10 times, starting with 1, you get 1,024. 1,024 of these. Okay. How high is that going to be? Well, it's over an inch. It's about an inch and a half. So 1,024 inch and a half would be 1,536. Yeah. 1,536 inches, which is close to 130 feet. Okay. Actually, a little more than 130. No, about 130 feet. If you double 10 more times, it's going to be 1,024 times that. Okay. It's going to be 1,024 times 130 feet. You're pretty much out of the atmosphere. Double a few more times and you're out to the moon. Okay. Again, just important aspects of the exponential function. Now, this is only the toolkit exponential function, but that's a good place to start. If we had the function y equals 3 to the x, if y is -2, 3 to the -2, well, if you look at the way the powers of 2 work, 2 to the -1 is 1 over 2. Okay, 2 to the negative 2 is 1 over 4, but 1 over 4 is 1 over 2 squared. So 2 to the negative 2 is 1 over 2 squared. 8 is 2 cubed, so 2 to the negative 3 is 1 over 2 cubed. 16 is 2 to the fourth, so 2 to the negative fourth is 1 over 16, which is 1 over 2 to the fourth. Negative exponent, a to the negative b, is 1 over a to the b. Again, something people should know coming into a pre-calculus class, but often don't understand even now, well, over halfway through pre-calculus class. Okay, that's an important rule. I'm going to use it here. What's 3 to the negative 2? It's 1 over 3 squared, which is 1/9. If x is negative 1, we get 3 to the negative 1, which is 1 over 3 to the 1, which is just 1/3. If x is 0, 3 to the 0 is 1. If x is 1, 3 to the 1, that's right, 3 to the 0 equals 1. 3 to the 1 equals 3. X equals 2, we get 3 to the second equals 9. If we wanted to do the graph of 3 to the x on top of the graph of 2 to the x, we start, let's say, at negative 2 with value 1/9. Now, this line here is y equals 1/4. Half of a fourth is an eighth, and a ninth is a little less than that. So we're going to have a point down here pretty close to the x-axis, although we never do get to the x-axis. Okay? And when x is 1, we get 1/3. Well, this is 1/2. Down here would be the line for 1/4. 1/3 is between 1/2 and 1/4. So we'll squeeze it in here. We won't try to be too accurate. Okay. When x equals 0, y equals 3 to the x is 1. When x equals 1, y equals 3 to the x is 3. Now, where's 3? Well, here's 2, here's 4. 3 is halfway between 2 and 4. So I would have a point about here when x equals 1. When x equals 2, y equals 3 squared, which is 9. You know, I did something ignorant here. I wrote this as y equals 16, and I was just doubling the 4. This line should have been y equals 8. I apologize for that. And y equals 16 would be up here as high as I can reach and so, as we said. Okay. Now, again, 3 to the second is 9. And what I was about to say is 9 is a little bigger than 8, and we've got y equals 8 here. Well, we didn't because I labeled it y equals 16, but it's y equals 8. Okay, so y equals 9 would be up about here. These are the points on the graph of y equals 3 to the x. And we see that y equals 3 to the x is less than y equals 2 to the x. When x is less than 0, so the graph of the 3 to the x function is lower than the graph of the 2 to the x function. But then it becomes higher, and it starts going up much more steeply. So here's your y equals 3 to the x graph. Now, you don't need this right away, but you're going to need it pretty soon. There is the exponential function. Okay? The exponential function is y equals e to the x. So I'll just kind of put this in red letters. y equals e to the x, where e is a number. It's an irrational number. It just keeps on going. It's 2.718, that's all right, but it's 2.718281828. Seems like the 1828 is repeating, but it doesn't. Okay. After that, you don't get another 1828 for about a mile. Okay. E to the x is approximately 2.71828. This means that the graph of e to the x lies somewhere between the graph of 2 to the x and the graph of 3 to the x, because of course 2.718 is between 2 and 3, somewhat closer to 3. So if we wanted to do a graph of the e to the x function, it kind of goes in, sandwiched in here between the 2 to the x and 3 to the x function. Maybe it does something like this. The exponential function has an important property. That is, and you don't have to remember this, it's just something you learn in calculus. But the reason it's so important is its rate of change is always equal to its value. So the rate of change, the instantaneous rate of change of the exponential function at x equals 1 is the same as the value of the exponential function at x equals 1. Believe me, that makes exponential functions pretty easy, one of the easiest functions to deal with in calculus. It's easy to integrate, it's easy to differentiate, but you won't know what that is until calculus. So I'm not going to go on talking about it. This isn't a particularly well-drawn exponential function. It should be closer to the 3 to the x function. It should go through a point right about here. It's a little too far to the right. It doesn't really hug the 3 to the x function that hard, but closer to the way I drew it. So don't take that as a literal graph. Those are important exponential functions. And here's how we make tables and create graphs. Now there's another exponential function. What about the function y equals 2 to the negative x? Can we make a table and construct a graph for y equals 2 to the negative x? Well, here's x, here's y. We'll use x values, -2, -1, 0, 1, 2. Can you, if you're in class, you're going to sit down and make a table for this, and I circulate around and see how it works. If you're a distant student or for some reason using the video, you want to pause here and do this table. So please do that. Okay? You've had a chance to do that. If you still haven't done it, pause and do it because I'm going to do it for you. Okay, if you weren't able to start though, let's say x equals -2, then what's y equals 2 to the negative x? Well, it's 2 to the negative x, which means it's 2 to the negative of -2, which means it's 2 to the second, which is 4. If x equals -1, y is 2 to the negative x. So there's 2 to the negative, and what's x? It's -1, which is 2 to the 1, which is 2. 2 to the -0 equals 2 to the 0 equals 1. Then we get to x equals 1. It's 2 to the -1, which is 1 over 2 to the 1, which is 1/2. And when x is 2, it's 2 to the -2, which is 1 over 2 to the second, 1 over 2 squared, which is 1/4. Okay, that's not overly difficult, but you got to get used to the idea. So what is the graph? Okay, what's a graph look like? Well, to draw a graph, you're going to draw a y-axis. You're going to notice that all your x values are positive. So you don't need to have a lot of y-axis down below the x-axis. So here's your x-axis. Here's your y-axis. X values are -2 to 2. So I've given you a start. So if you're in class, well, let's make a graph. Try to make a better one than I did, because I think this one is a little closer to the y-axis than this one. I didn't get these. The y-axis is not exactly halfway between 2 and -2. But yeah, try to draw a little better graph than I have. So please do that. And if you're in class, I'm going to circulate around and look at your work. Okay, now people typically do fairly well with this. As you saw me do before, I'm going to draw a line for x equals 1, -1, and a value for x equals 1. My biggest y value is 4. I'm going to draw a line here for y equals 1. And then my y values are 2, 1, 1/2, 1/4. Well, cut 4 in half, you get 2. Cut 4 in half, we're going to come down halfway from 4 to the y equals 0 line, which is the x-axis. And that's going to put y equals 2, maybe about here. And then we cut 2 in half to get 1. Means we go halfway from here to here. Halfway from the y equals 2 line to the x-axis. There's the y equals 1 line. Then we have y equals 1/2. I'm going to draw the y equals 1/2 line. And then half of that is 1/4. So halfway between the y equals 1/2 line and the x-axis is the line for y equals 1/4. So now I have a grid, lines for every x value and for every y value, and it's very easy to construct that grid. Now draw my points. See, when x is -2, y is 4. Well, there it is. -2, 4. When x is -1, y is 2. So here's the point, -1, 2. When x is 0, y is 1. Well, here's the point where x is 0 and y is 1. This is a point 0, 1. Then 1, 1/2. So when x is 1, y is 1/2. So I'll label that up here, 1, 1/2. And then 2, 1/4. So there are my points, and it's very easy to sketch a smooth curve. I'm going to sketch from right to left so my arm doesn't get in my way and make me miss something. You get a nice smooth curve. It's very easy to draw through all 4 points. Even though, my scale over here was a little tighter than the scale over here, it still gave me a pretty good looking curve. All right, well, what's a lesson here? Remember that the y equals 2 to the x graph looks like this, and the y equals 2 to the negative x graph looks like this. Well, this graph is just what you get if you took this graph and reflected everything about the x-axis. So I'll emphasize that replacing x by negative x flips the graph about the x-axis. Another way of saying that is f of negative x flips f of x about the x-axis. Now, there are other transformations you can perform with a function. You can vertically stretch it. You can horizontally compress it, or stretch it horizontally, compress it vertically. Gives you a wide range of exponential functions. Another thing about the exponential function, this exponential function, the 2 to the x function, or 3 to the x, or e to the x, has an asymptote at the x-axis. Its asymptote is the negative x-axis. By an asymptote, I mean we keep moving closer and closer to the x-axis, but we never get there. Because if we keep cutting our x values in half, or our y values in half at regular intervals, well, you can cut a number in half forever, and you never get zero. You get smaller and smaller numbers. You get numbers that might as well be zero for all practical purposes, but you never get zero. Y equals 2 to the negative x. Asymptote is at the positive x-axis. That means as you go further and further along the positive x-axis, the graph gets closer and closer to the x-axis, but it never reaches it. It never actually touches it. Although, if you keep cutting in half here, if you cut this y equals 1/4 in half about 1, 2, 3, 4, 5 more times, it's going to be inside that chalk line, probably 4 times. Give you a point that would be indistinguishable from the chalk line, because the chalk line has a finite thickness. If the x-axis was a perfect line, then it would have no thickness, and there would always be space between the halving, however many times you have it, there'd always be space between that halving and the x-axis, and the next halving and the x-axis. So there would always be space between the actual curve for y equals 2 to the negative x, or y equals 2 to the x, and the x-axis. That space would quickly become invisible. If you do 10 more subdivisions of this, you'd need a good magnifying glass to see it. And if you did 10 more subdivisions, you need a really good microscope. Okay. Okay. Anyhow, it's an introduction to some of the properties of exponential functions. This idea of a doubling at regular intervals. You see, at regular intervals, well, this one we saw before doubles every time x changes by 1. Now this one cuts in half. The y equals 2 to the negative x graph cuts in half every time we move over one more unit. So, okay, so we have a half-life. So another thing we can say about the 2 to the x function. I'll call it doubling time is 1 unit. 2 to the negative x the half-life is 1 unit. Half-lives are important. If you take some kind of medicine, some kind of, say, antibiotic, if you look up that antibiotic, if you look up the properties, they'll tell you what its half-life is, often 6 to 12 hours, somewhere in that range. I'm not sure what need would be overall antibiotics, depends what you mean by all antibiotics, but those would be typical half-lives. Meaning, if I take 1,000 milligram dose in one half-life, which might be 8 hours. After 8 hours, I'm down to only half of that 1,000 milligrams, okay, 500 milligrams. If I don't take it for another 8 hours, that would be 16 hours after I took the dose, I'd be down to 250 milligrams in my body. Okay. Now, of course, the directions probably say, well, every 12 hours, take another tablet. So after 8 hours, we're down to 500 milligrams. After 16 hours, we're down to 250 milligrams. We're probably 370 milligrams or so forth after the 8 hours. And we take another one. Now we're up at 1,300 some milligrams. So we're starting to build up an amount of antibiotic in our body. I think rather you should follow doctor's orders, but having the reason why you follow doctor's orders is very important. Okay. It makes you more likely to be compliant with your medication, and it gives you more insight about what's going on. If you're not interested in what's going on in your body, well, maybe you have good reason. You know, maybe your body feels really bad and you don't even want to know what it is. You just want to get better. In any case, it's, I think, profitable to be curious about these things and to understand why the dosages work the way they do, so that you're more likely to take the dosages on time and maximize the benefit of the medicine. This exponential process is very relevant to that. For finances, again, we talked about doubling time of an investment. There are a lot of things that tend to grow exponentially. Somehow, I got a lot of fruit flies in my kitchen. something in there that they're breeding in. We couldn't find it. And they're only a minor nuisance. But, we kind of got tired of inhaling them and stuff like that. Well, we weren't inhaling them, but, there were hundreds of them. So what I started doing is leaving a overripe banana peel in a jar. The gnats get into the jar and get to the banana peel. Then I take kitchen towel every once in a while and throw it over the jar. Carry it outside, release the fruit flies. Doors are closed, so they probably don't get back in. Some of them, I'm sure, do. I keep doing that. Well, what we see is the number of fruit flies keeps decreasing. Okay, why is this? Because a certain proportion of the fruit flies, maybe 10% of the fruit flies will get into that jar before I empty it again. And then 10% of what's left. And then 10% of what's left, and then 10% of what's left. It's going down by the same percent each time I empty the jar, assuming I empty the jar on regular intervals and all the conditions, temperatures and stuff are the same. It's not a perfect model, but there it is. So the number of fruit flies is going to tend to do this. It's going to tend to follow an exponential curve. And the number I release each time would tend to decrease as a result. So I just emptied it this morning and there are about 4 of them in there. And I don't see many of them around the kitchen. So I think we're just about to, if not eradicate the infestation, at least have it well under control. They're not really a bother right now. Back to the kitchen. If I cook something in a crock pot, turn on the crock pot, okay? The crock pot is going to put a certain amount of heat at a certain rate into whatever's inside of it. So the temperature is going to rise. But it's only putting in so much heat, so the temperature can only rise so much. So the curve that you get for the temperature is going to look something like this. And there's a certain temperature up here. A limiting value. Now this is an upside down exponential curve. You take this curve, you y equals 2 to the negative x curve, turn it upside down, and have the asymptote at this limiting value. And there you see what your temperature is going to do. Okay? Now, maybe that limiting value, depending on your device, okay, if I put the thing on high, the limiting value of the temperature would actually probably be somewhat over the boiling point. And the stuff is not going to go over the boiling point. Okay, so at some point that curve is going to have a cutoff. Let's just say if this blue line represents your boiling curve, then you'd say, well, that part of the curve is not relevant because it's not going to go over boiling. It's going to hit boiling, and then it's just going to stay there. And I hope your general science course in middle school taught you something about boiling points. Everybody else in the world knows it, so hopefully we do too. And there's another important line that you probably don't want to cross. Here's somewhere below boiling. The scorching point, where everything starts turning black and doesn't taste as good. So you probably don't want to go past the scorching point. So maybe you turn it to a lower value. So that your limiting value would be below the scorching point. Okay, so on a lower curve, you might have a curve like this whose limiting value is below the scorching point. Now, I didn't draw that particularly well, but hopefully you get the idea. Understanding the dynamics of curves like this can be very useful. Okay. Not that you're going to want to do precise calculations for everything you do, but having the concept could prevent you ruining a meal. Okay. And what's more important than a meal? Well, there are things. And maybe it prevents you from ruining those too. Let's sketch a few curves. One curve, every curve is going to go through this point, and every curve is going to have a doubling time. So I'm going to sketch first a curve whose doubling time is just the distance between these two equally spaced lines. So if I'm here and it doubles by the time it's here, it's going to go up to about here. Then it's going to double again. By the time it gets here, it's going to be twice as high as this, which means it's going to be up about here. Which means that on this curve, it's going to be up off the top of the board. So we're kind of done. Now, if we move to the left, before doubling to get this value, it has a value that's half as great. If we move to the left with a positive doubling time, we're going to be continuing to cut the value in half. So we have something that looks like this. And if this is 1 unit, then our doubling time is 1. If this is 12 years, then our doubling time is 12 years. The curve can represent any doubling time because I haven't labeled the values on this graph. Now I'm going to use T for time, and I'm going to continue to use Y for the vertical axis. Okay, instead of X, I'm going to use T because often your exponential function represents something that happens in time. All right, well, I could also draw an exponential function with a half-life equal to distance between two lines. So if I start here and go to half, there we have it. Take half of that, and half of that. Now, if I go to the left on something that's halving, it has a positive half-life. If I go to the left, one half-life, things are going to double. Go to the left, it's going to double again. So I'm going to get a graph that looks like this. And it's just nice and symmetric with the first graph that I drew. Now, if I have a function that has a longer doubling time, let's say the doubling time for this next function is 2 of these units. Okay, then if I start here, I've got to go over 2 horizontal lines before it'll double, and then 2 more before that will double. And then, of course, I could go 2 to the left before it cuts in half, and 2 to the left before it cuts in half again. And I get a curve. And that wasn't particularly well drawn. I'll blame it on the chalk. It was a little rough when I got right there. But I probably didn't have it headed right anyway. Okay. And if we regard to these units as a half-life, then it's going to have to, from here, it's going to have to go all the way over here before it cuts in half. It's got to go all the way over here before it cuts in half again. Then if it goes 2 units to the left, 2 vertical lines to the left, it'll double. And 2 more vertical lines to the left, it'll double again. Now, that's not a very well-drawn curve either, but you get the idea. If, for example, well, I'm not going to go that far. You're going to see examples of pictures that look kind of like this with prettier colors and with at least a couple more pairs of graphs. Okay. They're probably not going to be done in terms of doubling times. They're probably going to represent y equals b to the x with different values of b. So for example, if this curve is let's say y equals 3 to the x, then this curve, well, actually, I'm not going to write out what it would be. It would be y equals a smaller number to the x. Okay. It would actually be like y equals 1.732 to the x. If this curve was y equals 3 to the negative x, this curve would be like y equals 1.732. And the reason I use 1.732 is that's a very good approximation of the square root of 3. So if this is 3 to the x, this would be the square root of 3 raised to the x. But you don't need to know that. Just saying that in case you're interested. Different values of b. Like here we have b equals 3. Here we have b equals 1.732. There's more that I could say, but I'm going to say that that's enough for a basic introduction to exponential functions.